All right, so today what we're going to talk about is maximum matching in general graphs. So we talked about bipartite matching. We talked about bipartite matching in the previous lecture, and the result is a famous algorithm of Edmond's from 1965 called the Blossom algorithm. A minor sort of historical note here. So firstly, I mean, this algorithm is truly a work of art. It's really beautiful, and it's kind of amazing how it works. This is one of the first papers that talks about polynomial time. And this is one of the first papers that actually defines the class P. It's very interesting when you read the paper. He gives a polynomial time algorithm, and he spends almost a page. I'll see if I can dig out the paper, explaining why you should care about the algorithm when there's already an exponential time algorithm to solve the problem. And so he justifies it by saying that polynomial time is important. And that paper was actually one of the seeds of this notion of polynomial time and the birth of complexity theory. So it's a very significant paper from multiple sides. Not only is it significant just from the algorithm's perspective, this is one of the most classical and important combinatorial algorithms. It is also one of the algorithms that's provides the seed for computational complexity theory. So it's a very significant paper. So let's just recall what we're talking about. G, V comma E, simple, undirected, and a matching is a set of edges with disjoint endpoints. So if I have this graph here, put that in, then you could have the following as a matching. You have that edge and that edge, and that's a matching. And you'll see that there's no way that I can increase the size of this matching. But if I was more careful, I can actually have a matching of size 3. I could actually match, let me see if I can put it in red. I could have instead matched this edge, and this edge. Right? I could have matched it, and that would be the matching of size 3. And a perfect matching matches all vertices, and that just means that the size is n over 2. Right? That's called a perfect matching. And I will also define something that will be convenient. Hang on, sorry, let me just fix this, get it in focus. Right? So that is a perfect matching. Let me say the defect of a matching is the number of unmatched. These are also referred to as exposed vertices. That is called the defect of a matching. Of a matching M is the number of vertices that are unmatched. So for example, in the red matching, the defect is 0. But in the black matching, the defect is 2. The defect of the matching is the number of unmatched vertices. And instead of maximum matching, so we can, instead of maximum matching, we can talk equivalently of finding the minimum defect. And I'm going to talk about defect rather than the matching size because it's going to be a lot more convenient for a lot of the calculations to talk about the defect of a matching and to try to minimize the defect rather than maximize the matching. So the problem...
Does the defect have any relation to the kernel of a mapping?
Not the kernel of a mapping.
Like the kernel of a homomorphism, I was just thinking how like it kind of like keeps those identity elements the same, and these unmatched vertices are going to stay the same. They're not going to be affected in a way.
That not really. This isn't really. It isn't really finding. I mean, there are homomorphism finding problems in graphs, and this isn't really one of them. So I don't think that would be the best way of describing it.
Okay.
So the problem is to find the matching of minimum defect, which is the same thing as finding the largest matching. And this is the main problem, but what is going to be convenient is to actually study a special case from which actually the general case will follow. Just determine if there exists a perfect matching. So obviously, the first question is more general. You can use that to solve the second question. But I'm going to solve the second problem because it turns out that it's a lot easier to describe. And then once we do that, I'll tell you how we can solve the first problem. Okay, any questions about that? So we're going to talk about finding the matching of minimum defect. Note that we talked about this for bipartite graphs where we can convert the problem into flows, and we have augmenting, we have this notion of alternating paths, and I described the Ford-Fulkerson algorithm. Now Ford-Fulkerson does not work here because you cannot convert the matching problem into a flow problem. And so
Hi Professor, I have a question.
Yes.
So what's the point in converting max matching into minimum defect? Why would you?
It's just convenient to talk about. Like finding the matching of minimum defect is the same as finding the maximum matching.
Yeah.
And it is going to be convenient to talk in terms of the defect rather than the size of the matching. I can convert every statement about defect into one about size, but then the math just gets a little more complicated.
Oh, okay, I got it.
So you'll see, you'll actually, when I tell you the Tut Burge formula, you'll see what I'm talking about. Okay, any questions? Okay, good. So what I'd like to do at this point, actually, I don't need the notes right now. Let me just go ahead and say, can we characterize when perfect matchings exist, or find obstructions to perfect matchings? And so a very neat idea, which was introduced by Tut and Burge, is the following. So let's take a set of vertices, I'm going to call it R. So it's kind of like, think of remove R from the graph. So R is a subset of vertices, right? R is some subset of vertices. So what happens when you remove these vertices? You get a bunch of connected components. Okay, I'm going to draw them as circles and squares. I'm going to tell you why. So these are connected components of odd size. And these are connected components of even size. Okay? Now here's what you know. Suppose you take any matching. Take any matching. Right? So there are things that are matched in here. Can all these vertices be matched internally? Can all of these vertices be matched internally?
What do you mean by that? Like, is there a perfect matching within each group?
Exactly. So suppose you took any matching. Could everything inside be perfectly matched?
Not for the bottom left, right?
Not for the bottom left. Why?
With the 3 inside them?
No, so these have even size, these have odd size. So here you have an odd number of vertices. So if you look at any matching, there must be one vertex that is not matched internally. So matching is like pairing vertices up. If you pair up the vertices within a component of odd size, someone is left behind.
Yes, sure.
Does that make sense?
Yeah.
So each component here has got a vertex who's left behind within the component. Where could that vertex be matched? Now, if you need to match that vertex, where could you match it to?
Outside the component?
Outside the component, and the only option is within R.
Yeah.
So let's call this V. If V is matched, it is matched in R. Why can't V be matched to some other component? Why can't V be matched to a vertex in another component?
Then it would be one of the connected components, right? Of the even.
Exactly, because these are separate connected components. So if it is matched in R. If it is matched. Okay, does that make sense? Now, if there are more components of odd size than R, what do you know? If there are more components of odd size than the size of R, then what can you say about... Yes?
So there's always going to be one left over, right?
There's always going to be one left over, and that tells you that there cannot be a perfect matching. Right? If there are more odd components than R, then there cannot be a perfect matching. I'm going to write this down, but I want to make sure that you understand it. Does that make sense? Okay. So let me write this down. Please stop and ask me questions if some of this is not making sense. Okay, so I'm just going to write this down. I'm going to say, so I'm going to define, let OC of G minus R be equal to, this is set minus, is the number of odd connected components on removing the set R, right? R is some subset of vertices. So the claim, which I've just made, is that the minimum defect is at least the number of odd components minus the size of R. Right? The minimum defect is at least the number of odd components minus the size of R. Right? Because no matter what you do, you'll have at least that many unmatched vertices left in the odd components. This is the best you could hope for. For the question as to why talk about defect rather than size, well, the same thing in terms of size would be that the maximum matching the maximum matching size is actually at most half of n plus r minus this. You'll see that this is easier to parse than the latter expression. They're the same thing, they're equivalent. They are equivalent statements. But the first one is just easier to talk about, and that's why I talk about defect as opposed to the max matching size. It's nice to think about vertices that get left behind than to count the number of things that actually get matched. Okay. Does this statement make sense?
Sorry, a question I had is, so when you get the connected components, even the even ones, how do you know that they're going to be a perfect match?
Good question. You don't know they're going to be perfect matched. You don't know what's going on within them. So this is only a lower bound. Maybe the defect is more. That's why I said greater than equal to. Does that answer your question?
Yes, thank you.
Good. So I can also say the minimum defect is at least the maximum over all subsets of V of this quantity, the odd components, right? Because this is true, the claim is true for everything. This is an exercise that I'm going to leave, right? So for those who are wondering what kinds of exercises, I'm going to say, okay, write out a proof of this condition. That's the kind of thing that I would have as, the basic exercises. Okay, so there's that statement. And there was a very good question asked, which is, well, this is just a lower bound. I mean, how do you know what the matching is doing within? Maybe it's actually leaving certain vertices over here. But it turns out, quite remarkably, that there's a theorem essentially by Tut in 47 and Burge in 58, and this is known as the Tut Burge Formula. This is actually an equality. It says the minimum defect is actually equal to the maximum of this, the odd components minus the cardinality of R. That's pretty remarkable. Because this is kind of amazing, right? You don't even worry about what's happening in the even components. You don't know. But if you maximize this quantity, it turns out that's exactly the min defect. The proof of the statement is not long. I'm not going to do a proof of this statement. Instead, we'll see that the Blossom algorithm will actually provide a proof of the Tut Burge formula. But we will be using this. I'm going to refer to the first statement as the easy Tut Burge. Right? It's the easy condition. The easy Tut Burge just says the min defect is greater than equal to the odd components of G set minus R subtracted with R. Okay. Any questions at this point?
Sorry, it was a bit laggy when you wrote the second box. Can you describe how is it different than the easy one, the max portion of it?
It's identical. It's the same thing. Over here, I was just saying that it's equivalent. I was just saying that for all R, the following condition holds, which is just the same thing as the box. What is remarkable is the equality. I don't know, raise your hand if your mind is blown. I mean, I don't know, when I saw this the first time, I was like, what? That doesn't even, that's incredible. Like, how can that even be? Because your maximization doesn't even look at what the matching is doing. It seems to just use this very simple bound. And yet, when you maximize it, it turns out to be exactly the min defect. We are now going to use the easy Tut Burge to design an algorithm. Okay, so now, questions? Questions?
Oh, the max is saying for all R find the difference that gives you the largest value, and that's the theorem that ends up becoming. Oh, wow.
That actually is the minimum defect. So even though the right side doesn't talk about matchings, right? It just talks about, I mean, it's sort of talking about matchings, but it's ignoring the even components. It's ignoring everything there. It's even ignoring what's happening in there. Just saying there's one vertex that has to be left behind that has to be matched in R. That's what it's saying, right? It's a very simple condition, and I could explain this condition in 2 minutes. We wrote this down over here, which is a relatively easy exercise. But then, remarkably, when you maximize it, which is again, this inequality was easy, but it turns out to be an equality. Right? Which is, it's remarkable. So this was, again, discovered by Tut Burge 70 years ago. All right. So now let's move to the Blossom algorithm. There are two key ideas in the Blossom algorithm. So I'm going to show you the key ideas, sort of walk through them, and then I'll write out the Blossom algorithm. And depending on how time goes, we'll see how far I get. But what I want to do is to really explain the key ideas as opposed to writing out the nitty-gritty details of the proof, some of which I may leave as exercises. What I want to do is express the key ideas, and so let's go to idea number 1. And this is one that by now you will probably understand. It's called alternating trees, which is just a generalization of the alternating path. So let's sort of, at this point, I don't want to think about a specific algorithm, I want to think sort of abstractly. Suppose you have a matching. Suppose we have a matching M. So right now it's a partial matching. We're trying to see if it can become a perfect matching. Initially this matching would be empty. And we're going to try to increase the size of the matching. And we want to increase M. Potentially by finding an M augmenting path. Right, so we want to find this augmenting path. I'm going to describe the alternating tree. So we start from an exposed. Remember, exposed is the same as unmatched. We start from an M exposed vertex that I'll refer to as little r, because that is the root. Actually, let me refer to it as actually little s as the source. This is like the source of the tree, and build an alternating tree. So what is an alternating tree? So let me draw this. So here is my source S. I'm going to have some edges that come out, go to vertices. So I'm going to color code this, and this is going to be convenient. So I'm going to color code this. So this is black. So the source is going to be, oh, bummer. Actually, I'm sorry, I wanted to make it blue, and it's important that I make it blue. So I'm going to make it blue. Sorry about that. And then the colors are going to alternate. So then the next ones, they're going to be red. So it starts from a source. S is exposed, which means that S does not participate in the matching. These edges are going to be matching edges. Right? And then I follow this. And this is going to have some things that it forks into. So I'm going to build a tree of this one. The algorithm is going to build a tree of this one. And these I'm going to color blue. Then it's going to go into red.
those second level, why aren't they red also on the other edge of the matching?
These?
I thought, is blue not like exposed vertices?
No, blue is not exposed vertices. It's just, I'm going to color the first one blue. They're not exposed vertices. It's just the first one that is colored blue. And then these are going to go into matchings. So the idea, the way this works, the way the alternating tree works, is it starts from a source. Now, the coloring is going to be convenient for some stuff I'm going to talk about later on. So let me just sort of color all of this. Okay, so this is what an alternating tree is. It starts from the source, it takes an edge which is not in the matching, then takes a matching edge, then something not in the matching, then the matching edge. And it keeps doing this until, let's say, at some point you have some alternating tree. So this is the alternating tree. Now you have, so let me call this tree T, BT are the blue nodes or vertices, and RT are the red nodes. So the blue nodes are at even distance. The red nodes are at odd distance, right, from the root. For odd distance, so blue is even, red is odd. The red nodes have one child given by the matching. The blue nodes, they can have many children. Maybe they just have one, maybe they have many. Could be anything. This is an alternating tree. So you could imagine we're going to start from a vertex and we're going to try to build an alternating tree. Why are we building an alternating tree? Because we want to find that alternating path that's an augmenting path. And we're going to sort of use this tree to build, just like you would use, BFS or DFS. This is a very specific tree, right? It takes an edge that's not in the matching, then takes a matching edge, then takes something not in the matching, then takes a matching edge, so on and so forth. Okay, any questions about this? This is what an alternating tree is. And I'm going to now tell you how you're going to sort of build the alternating tree. You could imagine just starting from the source.
We never end on a red vertex, right? Because they always have one children.
Good point. So we will never end. Whenever it ends, it always ends at a matching edge. So which means the red node will always take you to a blue node. Now you might say, what if you find something? Okay, so let me ask you this question. Now, suppose you find a neighbor which is not matched. What happens? Draw this. Let's say you go here. So you find some edge, and suppose this was not matched. What do you see from S to this vertex?
An alternating path?
It's an alternating path, so you can flip. And if you can flip, you would increase the matching. So you've increased the matching. And once you increase the matching, you would go and restart the whole procedure. You'd say, okay, I increased the matching, I'm going to go back. I'm going to go back and find an exposed vertex in this new matching and redo the whole thing. But this is the neat thing, right? If you find a vertex which is not part of the matching, you find an augmenting path. And once you find the augmenting path, you can do the flip and you would increase. Good. So we did case one. So we did. Yes.
Sorry, but you can make that assessment at any level of the tree?
Good point.
Like at the first blue, I guess, or second blue, sorry.
Even at this blue, this is blue, sorry, it was supposed to be blue. You could even do it here. If you found something that was not matched, you say, okay, I'm just going to match us to that guy and move on.
Right.
You could do it here. You're right. That's a good observation. So it can happen at any level of the tree. It can happen there, it can happen there, there. So it's not really like a BFS tree the way you would think about it. It's not like you're doing it in levels. You're just kind of doing this in an ad hoc basis. Like at any vertex, you just go ahead and see if you can extend it.
I see. It looked at first like we had to build the max tree.
Yeah, so it's not like you're building it like, whatever, root upwards. You can just sort of build it in any arbitrary fashion, although it might be convenient to build it. If you were to write code, you'd probably do it in some way in which you scan the entire adjacency list first. Right? It's natural that you would do that. But it doesn't matter which order you build it in.
So I have questions. So is this alternating tree a balanced tree?
It's not balanced.
It's not guaranteed to be balanced.
It's
right?
not guaranteed to be balanced. It's not binary because red nodes only have one child. Blue nodes can have as many children as the degree of the vertex.
Okay.
Right? There is no BFSQ. It's just a tree that you're building on the graph.
But it looks very similar to the red-black tree. So what property do they share?
No, it is not a red-black. No, a red-black tree, that is a binary search tree where there are values at the nodes. This is nothing like a tree data structure that you would use for searching values. This is just a subgraph of the graph.
Okay.
You can think of it as it's some kind of like a spanning tree, although it may not necessarily be one.
Okay.
Okay, but this first, okay, so the question now is, okay, I'm just going to keep this picture up here. And what we want to do is we want to extend the tree. So how do we extend the tree? So remember, we said that we always will end at a blue vertex. So we start from a blue vertex B in BT and consider an edge. This is not a tree edge, this is just an edge BC where C is not in. Okay, I'm going to sort of abuse notation and say C is not in the tree. Technically I mean C is not in the vertices of the tree. Maybe I should just be precise. C is not in VT. This is the vertices of the tree. Right? So suppose you find some edge like this, or like this, or like this, where this is not in the tree, from any blue node. Now there are two cases. The first case we just discussed. C is M exposed. Then as we discussed, we found an alternating path. So flip and increase M. Now what the algorithm actually does will then just go and restart the entire thing from scratch. So you flipped, you're done. You increased. Case 2, C is not M exposed. What does that mean? It means C is matched. That means C is matched. So maybe this vertex is matched, which means CD is an edge in M, and CD is not in the tree, because this is a new vertex. So the matching edge could not be in the tree. And so now what you do is you extend the tree by adding both edges BC and CD. Okay, so I'll just...
How could, if it's matched, they're not disjoint, the blue vertice? So the blue vertice ends on a match, and then you're saying it's also part of another match to CD?
No, not this is... So maybe this is the point. This is not part of the thing. You're looking at this vertex here. That vertex is part of a matching. Remember, I started with B, so let's call this B here. Let me give some names here. So this is B. And then I'm looking at C, which is some neighbor, which is not in the tree. If C was exposed, I found my alternating path. But if C is part of the matching, then I get to extend the tree. So then what that means is then I'm going to color this node red. And then I have my matching here. I have that.
Thank you for that explanation.
I'm sorry?
Thank you.
Yeah. Sorry, dealing with all the colors, it's a bit, takes a bit of time, but I think it makes it much more clear. Okay, does this make sense? That's how you extend the tree. Cases 1 and case 1 and case 2. Let me see if I can zoom out a little bit more because that allows me to sort of put more, maybe I can put it side by side.
Question I had
Yes.
was in the case when we flip it, do we start with a new S now? Because
Exactly. You would just go ahead and restart the entire procedure from scratch.
Okay.
You would just like redo everything. Okay, I'm just gonna put this.
Would the S be random, or would it be the C that you found?
It's arbitrary. You can pick anything that you want. It's arbitrary. You can just pick any C, any S to start with. Okay, so case 1 and case 2, if you find, so what this means is, sorry about this, I'm trying to sort of see what is the best way that I can get everything in place. All right, maybe I'll just stick with this. Right? So if you find any such edge, then you're either in case 1 or case 2 and you can go ahead and make progress. So at some point we're stuck. So at some point, no progress. What does it mean that there's no progress? It means that for all blue nodes, the neighborhood of the blue node is contained in the vertices of the tree. Right? What this means is, so I'm actually just going to, let me just go ahead and sort of complete this tree over here so let's just say you went and then you extended all of these, right? Extended all of these. And so now you have your tree here. And you have your node there. And those are also blue. Okay, now what's going on is that if you look at any blue node, its neighbor is already in the tree. The red node may have neighbors that are outside. Right? So this is not your typical BFS tree, right? Your red node could have things that are going out. But you are not allowed to extend from the red node. You are only allowed to extend from the blue nodes. So the red node may have things that are outside. And this is what complicates things, because who knows, maybe there's some alternating path that you can form by looking at some of those nodes. Right? But you're not allowed to extend from the red node because it doesn't make an alternating path so easily. Because if you found some node over there, it's not an alternating path. So at some point, we are stalled, we're blocked, if for all blue nodes, the neighborhood of the blue node is actually in the vertex set. Let's see how far I can get by just putting this side by side. Sorry. I'm just going to keep this over here so I can refer to it when I need to. Okay. And this is going to give us our first crucial definition here. A tree is frustrated. A tree is frustrated if for all the blue nodes, the neighborhood is actually in the red set. So what this means is, so at some point you're stuck because for all blue nodes, the neighborhood is in the tree. But it could be anything. It could be maybe a blue node is connected to a blue node is connected to a red node, you don't know. But a tree is frustrated if all the blue nodes, their neighborhoods are entirely in the red set. Does that make sense? That's what a frustrated tree is.
Why is that not now the min for maximum matching? Like, why is it frustrated rather? Like the other algorithm, after you keep flipping the alternating paths with the bipartite graph, you're at the maximum matching.
So it's a good question. What happened? Okay, so let me answer that question shortly once I do this. Like, what is it about bipartite graphs that makes a difference? A very good question, and I'm going to answer that right now. But first, I want to sort of make sure that you understand this notion of frustrated. A tree is frustrated if for all the blue vertices, the neighborhood is in the red set. Right? That means that all the edges look like this. From the blue, they go into the red set. Maybe something like this. And this happens for all blue nodes. For all blue nodes, their neighborhood is in the red set. Now,
I just keeping the high-level goal in mind. We're trying to increase this alternating tree right to see if it's possible, or not to see if it's possible, to see if this graph that we've constructed from is in fact a perfect matching, right?
We are trying to detect if the graph is a perfect matching. We are using this as a mechanism to increase our matching size repeatedly. At some point, this method fails to increase the matching size. What I'm going to show you...
I'm worried about the S. Won't the S always be unmatched, or...
So, good point. So you observe that the S is unmatched. So if you find an alternating path, then you can always match S. Maybe let me draw a picture here that may be useful. Let me see if I could draw this properly. Let's see one of my pictures over here.
I don't know if this is the right way to think about it, but I was thinking if the graph we started constructing from was in fact the perfect matching, then it would have to be the case that there would be some vertex that's left outside the graph that S would have to match to.
So this is not a graph, this is a subgraph, right? This is a portion of your graph. Does that sort of make sense? It is really a portion of the graph. It's not. Okay, so here is why there could be a problem. Let me explain this over here. Okay, so suppose the following was true. Okay, I'm just going to draw these edges here. Suppose this edge is present, and this goes to something that's unmatched. Now, note that your alternating tree does not allow you to extend from the red nodes, because when you extend from that and you found something that's exposed, that's not an alternating path. But if this edge is present, there's another alternating path that goes like this. So there's an alternating path of length 5, which kind of goes down the tree and up the tree and then goes out. How are you going to discover such an alternating path? Indeed, the Blossom algorithm gives you the mechanism to do it. So what we're going to show is how to discover more and more complex alternating paths than just the ones by extending the blue nodes.
So in this case, we failed to find the correct path because of the way that we do our tree search?
Exactly. The way that we've set up the tree, we're stuck. And so how do we get out of this place? I mean, a priori, we don't know what the right choices are. So the remarkable thing about the Blossom algorithm, it just says make a bunch of choices and it'll tell you how to fix the problem.
So it's possible that, like, with a depth first search, we end up in a frustrated state, but in a breadth first search, maybe we'll find...
Yeah, but wait, no. So let me about this. Okay, let me explain. Frustrated does not mean that we're stuck. Frustrated means that you're stuck and the neighborhood of the blue is always red. why do I care about this? So I'm like, okay, I need to write this down so that you see this. So the claim is, suppose G has could be a partial, not necessarily the full matching, a partial matching M and an M alternating tree that is frustrated. Then G has no perfect matching. Okay, this is the remarkable observation. It says that if your tree is frustrated, then there's actually no perfect matching, so you can stop, because our aim was to find a perfect matching. And if the tree is frustrated, we can actually prove that there is no perfect matching. Now,
Okay, so the graph, the example that you gave on the other page, that's not a frustrated graph.
it's not frustrated because there's this edge over here, from blue to blue. But if all the edges were from blue to red, if all the other edges were blue to red, then it's frustrated.
Okay.
Okay? Alright. So any thoughts on the proof of this? Remember, I showed you how you could lower bound the defect. So here's our tree. Suppose this edge was not present there. I called it R for a reason, not because I wanted to color it red. I mean, I did want to color it red. It's because I also defined this with respect to R being a set that you can remove. Okay? So let's look at this tree here. We said it's frustrated, which means that all the blue nodes are only connected to the red nodes. Suppose you delete all the red nodes. What's left? So take this tree, delete all the red nodes. What happens to the blue nodes?
Are they odd components of size 1?
They're odd components of size 1, exactly. Right? Because they're only connected to red nodes. So they're odd components of size 1, precisely. How many blue nodes do you have compared to the red nodes?
One.
Sorry, what?
One more than the red, right?
You have exactly one more than the red because of the root. And so you have one more odd component than the number of red nodes. And therefore, by the easy Tut Burge condition, the min defect is at least 1. It could be more than 1. It's at least 1. And so there is no perfect matching. Beautiful. Right? So if the tree is frustrated, what you do is you remove RT. All blue vertices become singleton components, singleton connected components. And the number of blue nodes is actually equal to the number of red nodes plus 1. Hence, the number of odd components in G minus R is at least PT. So it's number of red plus 1. And by easy Tut Burge, the defect is at least 1. And that ends the proof. So if you have a frustrated tree, then you know that there is no perfect matching and you can just end. Right? Because right now our aim was just to find a perfect matching.
Isn't the number of blue nodes the number of red nodes, at least the number of red nodes plus 1 and not equal to the number of red nodes plus 1?
it's exactly equal the way you construct it, because every red node is going to have exactly one child given by the matching.
But in this example graph, where you have that extra unmatched node that comes off of that top red node, is that considered a blue node?
That's not it doesn't have any color.
Okay.
Good question. Yeah, it has no color. So you're right that the number of odd components could be even larger, because the other nodes that are outside may have these odd components, but it's greater than equal to. Maybe that was your question, and you're right. It's greater than equal to. There are nodes that are neither red nor blue. Because of the way that you construct the alternating tree, you only extend from the blue nodes. And what it says is the tree is frustrated if the blue nodes are only connected to the red nodes. And when that happens, it's frustrating. You can end. And so where are we left? Suppose the tree is not frustrated, but we cannot extend. Suppose the tree cannot extend and is not frustrated, which means there exists a blue edge. A blue edge, which I'll say, it's like there's an edge B prime, where both B and B prime are in the blue set. And now what? And this leads to the second idea, which is the key idea of Edmond's, which is called the blossom. This is how and that I have described. That's an example here. So let's just say that that thing was B, and that was B prime. And so what we have over here is this odd cycle. It could also be something like this. It could be anywhere to anywhere. It could be maybe that to that. So if any such edge existed, then it is not frustrated. So I'm sorry that I should have put dashes, just to say that this is not an edge of the tree, but it's just an edge of the graph. It's an edge of the graph. Okay, this is a good time for me to pause. I'll pause the recording. I will answer any questions that you have. Okay, so at this point, I think, given the discussion, hopefully, mostly are people following? Like, raise your hand if things are by and large making sense here. Just helps to get some sense of, okay, good. So, mostly people are following. All right. Okay, so idea number 2 is the odd cycle contraction, and this is called a blossom. So Edmonds typically came up with fairly colorful language. I wouldn't say colorful, like very nice words for various constructs he had. So he called this a blossom. And what he said was, well, okay, let's go back to this picture. Suppose you have a blue edge, like this. Note that all the blue nodes are at even distance. So if you start from B and B prime, and you look at the tree path between it, you get an odd cycle. Note that if you start with these two, you get this odd cycle. If you use these two, then you get this odd cycle. When you have a blue edge, then there is an odd cycle in the graph. What this tells us, this is why Ford-Fulkerson and bipartite graphs are easy. Bipartite graphs do not have odd cycles. And so you can never end up in a situation where the tree does not make progress and is not frustrated. Okay? This is an important point. If the graph is bipartite, you can never be in a situation where the tree cannot extend and is not frustrated. And this is exactly what people are asking. Can you somehow make the tree always make progress to get the answer? In a bipartite graph, the answer is yes. As you build the alternating tree, eventually you'll get to the answer. But because of odd cycles, this gets stuck. So what Edmond said is, so this odd cycle here, Edmonds considered that like a flower of the tree. And this is called the blossom. So a blossom is an odd cycle formed by a blue edge. So a blossom is the odd cycle formed by a blue edge and the tree path. So let me call this B and B prime, tree path from B to B prime. Okay? And so his clever idea is you can contract the odd cycle. So I'm going to talk about this with a little bit of abstraction first, and then we'll talk about the blossom specifically. So consider some graph where there's an odd cycle. So here's an odd cycle, and suppose I have some graph here. So consider this odd cycle. Contraction, so this is G. And G cross C, this is contract by C. Contract by C is a new graph where you replace the C by a single vertex. And you keep all the other edges. So what happens is, how many vertices do I have here? So you keep all the other vertices, and you keep all the edges amongst them. And you keep all of these connections. You keep all the connections to this. Okay? So contraction is replace C by a vertex. And this is called a pseudo vertex. And keep all edges. You can remove parallel edges. Okay? Now there is a neat theorem. So suppose you take a matching in this graph. Okay? You take a matching in this graph. Let's go ahead and look at what the matching, oh, this is not a matching, I'm sorry. Oh, bummer. That was not a matching, so, sorry. Not that. Not that. So let's look at this matching in this graph. So you can take this edge here, and then you can take any one of these. You can take that edge. So you can start with a matching in G cross C. You can go back to G, and because this is an odd cycle, you can add those edges in. Remember, because this is a matching, there was only one vertex that participated in the original black matching, and so you can add these two vertices. The defect was 3, and the defect remains 3. What this means is if you contract an odd cycle, construct a matching here, you can go back and extend the matching, maintaining the defect. So the defect here was 3, the defect here is 3. Does this construction make sense? So in an odd cycle, when you kind of blow it up, one of the vertices gets used up, but then all the other vertices can be matched to each other because it's odd. Right? You use the fact that it's an odd cycle. You cannot do this if it was even.
The contractions might not always be possible, right?
No, you can always contract by anything. You can contract by any cycle. The problem is if you had an even cycle, the defect would go up by 1. But in this case, the defect will stay the same. So if there's a perfect matching here, you get a perfect matching here. So maybe let me draw that. Suppose there was this other edge. I'm really sorry, there was that edge over there. So then there would be that edge over here, and maybe there was another vertex here. Okay. So let's take a perfect matching here. So there is this perfect matching there and there. I could go back, I could just take all of these, and I would have perfect matching here. So if G cross C has a perfect matching, then G has a perfect matching. This is only true because it's an odd cycle. And so this is the claim. If G prime equal to G cross C has matching of defect D, then G has a matching of defect D.
So, and that's irrespective of the matching used to get into the odd cycle that touches the odd cycle?
That's irrespective of the matching that touches the odd cycle. So let's say if you had a matching that did not touch the odd cycle, then note that pseudo vertex would have contributed to the defect, and that will contribute to the defect again. So I'm going to leave the proof as an exercise. Slightly more challenging, but once you think about it, you'll see it. And it's because it's an odd cycle. If it's an even cycle, it's not true any longer. It's very, very neat. Like, so it's almost like amazing that all of this will match up, because the alternating tree got stuck because there's an odd cycle, but if you contract the odd cycle, then you can compute perfect matchings in what remains and go back to the original graph. Right? It's remarkable. Okay? And so the main idea of Edmond's was not the alternating tree, because people had the alternating tree going back all the way to Koning's theorem. The key idea is to contract the blossom and then proceed. Okay, so let me try to write this out. And I'm going to sort of draw a small example here. I don't want to draw a big one because it's going to sort of take up too much space. Let's see if I can quickly do this. Here's my matching, and say matching. Okay, and let me just color all the nodes. So this is red, 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 and blue. And let's just say there is some blossom. So what could a blossom be? So here's this. So here is my blossom. And maybe there was actually stuff going out from there. What you can do is you can contract this blossom, contract the blossom, and create a pseudo node. So the picture would then become like this. Here is your pseudo node, which is the blossom. And everything else looks exactly the same. Okay, so what this is the blossom, that's the blossom over there. Right, all the other colors remain exactly the same. Note that this blossom now has 4 children, right? Because it has this child over here and these 3 children from before. And of course, all of these are red. Yes, red. And these are blue. Right? And so you have this sort of picture here. Okay, this is the blossom. The blossom has now contracted. And then it turns out you can just proceed as before. Why would this help? And let me show you an example. Suppose this red vertex was connected to something that was unmatched. Here's the alternating path that you had from before, but you were not able to go up and down. Now it turns out you can, because you contracted that blossom into this big blue node. Now you have an alternating path just as before. So you can augment on this alternating path. The blossom sort of allows you to go up and down. And then once you find the matching here, using our previous claim, you can go back and extend the matching to what was there before. And then in general what might happen is, well, maybe there's an edge from here to here. So you can contract this to find another blossom, a bigger blossom. It's a blossom that has blossoms in its, like it's a blossom that has pseudonodes. And you contract that, and then again you try to do it. You keep trying to do this until you get frustrated. And once you get frustrated, you know there's no perfect matching. And because when you do a series of contractions and you have defect, that means if you go back up, you will still have defect. And that's basically the algorithm. I will write this down now in some more detail, but that's the idea. Questions? It feels like a bit of a magic trick. So let me try to sort of write this out. So does the notion of contracting a blossom make sense?
Yes.
Sash?
Yeah.
Could you explain what you mean by moving up and down?
Sorry, by moving up and down, I mean that, so to go from, I'm sorry, so what I should say is you have contractions. I would say opening up the contractions like going up. So you could go from this tree to this tree. This is the contraction. And going back, this you could think of as expansion. Right? So when you contract it and you get to here, if you can find a matching in this situation, like by augmenting, you can always go back and then you can get a matching of the same defect. So if you decrease the defect when you come down, you can increase the if you can decrease the defect after contraction, then you will end up with a matching of lower defect overall.
I see. Thanks.
And sort of conversely, if this tree is frustrated, or so let's say you do a contraction, and then this is going to be a blossom here, right? That's a blossom. So do another contraction. Right, so you do another contraction. So, maybe this thing was red over here, and there's something going on. And then eventually you get to some tree, like this. So note that once you do this contraction, this pseudonode here actually consists of a cycle with a pseudonode in of itself, which when you blow it up goes there. So it's like a huge structure. The blossom, when it opens up, it's like this flower, as he called it. This flower is like a huge object. But if here things are frustrated, if you get frustrated at any point, then there is no perfect matching. The key here, honestly, when you understand this, is to understand the ideas here. I will then write out a series of claims, which if you do as exercises, all of this will become clear. It's hard to sort of write everything out within an hour and a half, but I want you to get the basic idea. So when you have a blossom, contract it, and keep contracting. And why does the blossom contraction work? It's because of this claim here that says that after contraction, if there is a matching of some defect, then the original graph has a matching of the same defect. And what we'll show is, okay, so I have to show that when things get frustrated, there is no perfect matching. I have to show you that, which I will prove shortly. Okay, so I'm going to sort of...
Sorry, the
yes.
Contraction basically lets us, it solves the problem that we maybe took the wrong path. It almost lets one red edge, one red vertice have two match edges come out of it.
Kind of.
Like
Yeah, in some sense, well, another way of looking at it is the way we set up the tree, you were only allowed to extend from blue vertices. But once you contract, you effectively get to extend from red vertices as well, because you kind of combined it together. But the reason why all of this really works is because of this claim here. I will write down another series of claims, which is going to make this much more precise. So what do we have right now? I think I'm just going to write this out. You have the graph G, you have the matching M, you have the tree C, and then you have a blossom, which is the odd cycle C. When you do contraction, you end up with G prime, which is the contraction of C. You have M prime. So again, you can look at this picture here. When you contract this cycle away, all the other matching edges remain as they are. Everything else about the tree just stays the same. It's just this one cycle that gets contracted down. So M prime is just going to be M minus the edges in C, the M edges in C. Now you have another matching. T prime is the contracted tree. And the blossom is a pseudo node or a pseudo vertex. The blossom is a pseudo vertex. So now let me write down this claim formally. I'll say after contracting the blossom, M prime is a matching of G prime. T prime is an M prime alternating tree. And importantly, I'll call this is a pseudo vertex E. This pseudo vertex is blue. This is the pseudo vertex. So the pseudo vertex is blue, right? And as we described here, when you contract it, the pseudo vertex is going to be blue, because I think in some descriptions they call this the stem of the blossom, and you'll see that the stem ends at a blue vertex, and then you have your blossom. And so when you contract it, you contract to a blue vertex. But here is maybe the more crucial claim. After a series of blossom contractions, after a series of blossom contractions, all pseudonodes are blue. That's simply induction. All pseudonodes are blue. And this is the key. Every pseudonode is a connected set of odd size. Okay, this is something remarkable. I mean, this, to me, this was the genius of Edmonds, that he recognized this. So the first sentence is easy. First sentence is an easy induction. Is easy induction. Now, at any stage, the blossom is an odd cycle. Each vertex is either a usual node or a pseudo node. I apologize, I may have said pseudo vertex before and I have switched vertex and node. So let me just call it node. So it's either a usual node. Now, what is the size of a usual node? The size is 1. This is odd size. It's just 1. Or it's a pseudo node, which by induction is of odd size. So the total size, which is the total size after you contract the blossom, is a sum of an odd number of odd numbers, which is odd. Okay? So it says that if you have an odd cycle, now as you do this, remember what happens here is that after this contraction, this blossom actually has 5 vertices in it. 5, 6, 7, 8, 9. So this blossom has 9 vertices in it. And if you keep contracting these cycles which have blossoms, the overall size is always going to remain odd. Now you might say, why is that important? And we're going to use that fact to show that if you ever end up at a frustrated setting, then there is no perfect matching. That's what we're going to show. Any questions?
The sizes here we're talking about are just of the blossom, right?
The size, so think of it as, as you contract it, you keep track of all the vertices that you got. Like when you contract this blossom, the vertices involved are all the vertices in the entire thing that were part of this blossom. Which the blossom could be essentially like a collection of blossoms, so you have to open everything up. But that entire set, the whole thing, is odd. Now why is that going to be relevant? Because that's an odd component once you remove the red vertices. So once you remove the red stuff, if you're ever at a frustrated point, when you remove the red vertices, the blue vertices become connected components. Before they were singletons in the first argument, but now this blue vertex is just a connected component, but it's of odd size. And so again, you can use the easy Tut Burge formula. So I'm going to write this down as a lemma, and this is sort of the key lemma for the blossom algorithm. Consider graph G prime obtained by a series of blossom contractions. Let T prime be an alternating tree of G prime that is frustrated. That is frustrated. So this is the key. So T prime is actually frustrated. Then G, the original graph, not G prime, G has no perfect matching. And G has no perfect matching. This is the proof. And so note that there are two key things I want you to note. All the pseudo nodes are in BT, and every pseudo node is a connected set of odd size. So consider the red nodes in whatever tree you have at some point. This consists of usual or normal nodes. Remove RT. All blue nodes or pseudo nodes become separate connected components, they all have odd size. That's the previous claim. That's the previous claim. They all have odd size. So the odd components of G on removing the red set is equal to, is at least the number of blue nodes in your frustrated tree at that time. And this is RT plus 1 as we had before. So by the easy Tut Burge, G has no perfect matching. I want to emphasize here that you're applying the Tut Burge condition on the original graph, not on G prime. The reason why it works is because the red nodes are always just standard nodes, and the blue nodes are connected components of odd size, and so they're odd components, and you can apply the Tut Burge condition. And that is the remarkable part of this, of all of this. The fact that the blossom contractions always give you pseudonodes of odd size, so the Tut Burge condition will go through. It's almost magical how everything lines up in this proof.
We just showed we can always answer this, right? It almost sounded like at the start of this that we can't make progress, and then we won't get the answer. I guess we can't make progress to get the maximum matching, but we can always make progress to answer that there.
That there is a perfect matching. So actually, it turns out that with pretty much the same algorithm, with just a slight modification, you can actually get the size of the maximum matching. But the proof of that is a little more tricky, and it turns out that if you go through that proof, you prove the Tut Burge formula. We'll see. I might do it the next lecture, depending on what my plan is. But what I wanted to show you to make sure you understand is basically this idea of the basic blossom algorithm, right? And this is how it works, right? You keep trying to extend your tree. So maybe let me just walk through this, and we'll see. So you start with your alternating tree. You keep trying to extend it. So either you get an M exposed vertex, you found an alternating path, you increase the matching. If you find a new vertex that is matched, then you can extend the tree. So at some point there is no progress. Two possibilities. The tree is frustrated, in which case you know there is no perfect matching, you stop. Otherwise, the tree is not frustrated, there exists a blue-blue edge. And if there exists a blue-blue edge, then you have a blossom. So you contract the blossom, and then you proceed. And then you keep trying to extend the tree. So you switch between the contraction, the blossom contraction, and the alternating tree, and extending the alternating tree. So you do the contraction, and you keep doing contractions until at some point either you get frustrated, there's no perfect matching, or if you augment it, well then you can go back to the start. You can say, okay, I've increased my number. So I'll just sort of write this out maybe in a somewhat simplified fashion. I don't want to write entire pseudocode because it's going to take me too long. Hopefully you get the idea. So the blossom algorithm basically says, start with some matching. Start with a matching. Construct an M alternating tree. Keep extending until no progress. If we find an alternating path, then just increase M and restart. So then you say if the tree is frustrated, well then you output no perfect matching. No perfect matching. And I should say if M is perfect, then done. Then you're done. And otherwise the tree has a blossom. Contract and go to step 2. Right? You contract it and then you go back and trying to do this. And if you implement things properly, you can make this an O of Mn log n algorithm.
I thought in the first lecture you made the claim that a normal graph finding the maximal matching is is non-polynomial.
You mean is NP hard? No, that was vertex cover. The maximum matching is in polynomial time, but the vertex cover is not. I mean, we don't know, assuming P is not equal to NP.
So what is the time complexity for detecting blossom?
For finding a blossom is just linear time, right? Because it's a tree. And so you can basically look up the edges. If you index your tree properly, you can look up everything. You can probably look it up even in constant time. Because as you go along, you can just color the vertices blue or red, and then you look up a neighbor and check if it's blue.
So using a map would be constant time.
Yeah, you can do it in, if you use a hash table, do it in constant. You can use, or you can do it in logarithmic time using, using some kind of search data structure. You can just use a bitmap actually. You don't even need because the universe is finite here. It's just n vertices, so you can just use a map. Yeah.
I see, thank you.
So, and it's Mn because there are n augmentations. Right? That's like how many times are you going to restart? You can only restart n times because every time you restart, you've actually increased the matching size. And this is sort of doing all the contractions. I haven't told you how to do this implementation properly, but you can imagine that you can do this. You can easily get something like m square n just by doing some sort of very naive implementation. But this gives a polynomial time algorithm to determine if there is a perfect matching. And it turns out that to get the size of the perfect matching, all you have to do is that when you have a frustrated tree, instead of outputting it, you remove the frustrated tree and then you run the algorithm recursively on what's left. And it turns out the entire matching that you get is a perfect matching. The proof of that is a little bit more complicated. So I'll end here. I hope you... Yeah, sorry, question.
No, sorry, I was going to just let you know that we'd run over.
Yeah, so I'm going to end over here. And sort of I hope you enjoyed that. It's sort of an amazing algorithm. And so I'll take any questions.